So this table of reduction potentials is actually quite cool because it actually allows us to quickly analyze chemical reactions and predict whether or not the reaction will take place in a rather straightforward manner. Before, we would have to run these, we'd have to add up all the delta G's and all that other stuff. And so instead, we can turn to the standard reduction potentials and get a feeling for whether a reaction would progress in terms of will this oxidize that or what have you. So let's take a look at an example. What happens when you add molecular bromine, Br2, to an aqueous sodium chloride solution? All right, so we're dealing with two things, bromine and aqueous sodium chloride. And so the reaction we're looking at is, will the bromine act on the sodium chloride to produce chlorine gas and bromide ion? Now, for this we can turn to the reduction table, the standard reduction potential table. There's something called the diagonal rule. And basically what it says is that anything that is lower on the reduction table will be oxidized by something to higher up on the periodic table, as follows. Anything over here will oxidize anything below it over here. So for instance, if we take a look at our example here, liquid bromine, elemental bromine, can oxidize anything underneath it. It'll actually turn hydrogen peroxide into oxygen. It'll basically couple these reactions. This will be the forward reaction. It'll drive anything below it backwards. So let's take a look at chlorine. We don't happen to see chlorine, but if you actually look up on the periodic table, you see that the chlorine will be reduced to chloride ion, but it's further up on the reduction potential table. So therefore, what that means is the chloride will not be the chloride will not be oxidized up to chlorine gas. But if we look at iodine, the iodine is down here. The bromine will convert the iodine ion into molecular iodine, which would be part B of this. So we look, part B says, will molecular bromine react with iodine? And we see that the iodine is lower on the periodic table to the left and drives the reaction backwards. So depending on which reactions that we're looking at, one of them will take place. And so we can use this as a guide for our whether or not a reaction is quickly and easily spontaneous. If the reaction higher up on the periodic table is progressing as written than the one on the lower portion of the periodic table, then we can suspect that this reaction will be spontaneous. Converse is true too. If this reaction were reversed, it might not be a spontaneous reaction. So that's one thing you can do with the reaction. Another thing is, as we saw last slide, was that we can use this to predict cell potentials. To predict reaction spontaneity. And usually, we're dealing with redox reactions, though not always. So let's take a look at another example. The other one deals with examining galvanic cells. Galvanic cells are precursors to batteries. Each galvanic cell is composed of half cells, which are analogous to our half reactions that take place. So let's take a look at one material. If you take silver ions, silver metal, and you plunk it down into a beaker filled with a silver nitrite solution, and this is a 1 molar, and then another solution, say with some magnesium ions, magnesium metal, and you connect them with a wire. We almost have a battery. You could put a voltmeter on here and measure the potential between those two materials. Now, if we take a look over at our periodic table, we see that our standard reduction table, we see that magnesium is much lower on the standard reduction table than silver. Now be careful, there's two silvers. There's one that deals with silver chloride in the solid state, and one that deals with silver ion. It matters in this case. There's a slight difference in potential. So we see that the silver is much higher on the periodic table. What that means is the silver ion will drive the magnesium to form magnesium ion, precipitating out silver metal. So if you throw the chunk of silver, the silver would precipitate out. This reaction will be driven. And we can actually calculate the cell potential for this magnesium-silver material. So if you go into the lab and you set up these two solutions, again, everything under standard state, again, this will be equal to the E1/2 of the oxidation plus the E1/2 of the reduction. Now, we can look at this system and we see that the silver be our reduction preferentially. Silver plus 1 electron goes to silver solid. This will be our reduction. Again, it's higher in the periodic table, more likely to be reduced. And that means the magnesium, lower on the periodic table, more negative, will be our oxidation. Magnesium plus 2 goes to magnesium ion plus 2 electrons. And this one is positive 2.37 volts. So the combined voltage of this cell with 3.17 volts. So that means we should be able to go to the lab and measure this cell potential. We'll hook up a voltmeter to each of these, and you will find that it will read 0 volts, not 3.17. So here's the problem. As this silver reaction is progressing, silver ions are going to be consumed in the process. The silver will plate out and need to suck up electrons for that to take place. Right? So electrons will need to move between these two systems. So the electrons will move from the material undergoing oxidation to the material undergoing reduction. And at the same time, because the electrons are moving. They're coming from somewhere. They're coming from the conversion of this magnesium metal into magnesium ion. Now, as this is taking place, what that means is, as the electrons migrate over here, this solution becomes more and more deficient in positive charge, more and more negatively charged. It's missing a bunch of silver. This one now has an excess of positive charges in terms of the magnesium. And so the reaction will stop because we are building up charge in two separate locations. I said the universe doesn't matter, but that's kind of a lie. What needs to take place is there needs to be some way to balance the charge. We're not just moving electrons. We need to somehow balance the charge out. And for this, there's a third component in most of these cells that we call the salt bridge. Usually this is some sort of conductive medium that is filled with a salt, like sodium chloride or sodium nitrate. Some sort of inert salt. And what happens is, as these ions flow out, negatively charged species like the nitrates or chlorides will move into the solution to balance out, and positively charged species like the sodium will move in to the solution, balancing out the charge. So integral to separating the mass balance, the mass of these reactions, is this idea of the salt bridge, this feature that balances out the charge. So we have electrons moving to one side, and so for all the electrons that you move, you need to balance that out by adding some sort of ion. Or you can also balance it out with some sort of negatively charged species moving. Usually sodium and chloride are fine. So the salt bridge is very important. It's a very important component. Now, in your car battery, it's usually something like battery acid. Right? It's the acid that acts as the salt bridge. So, but in other media, like your cell phone battery, it's usually some sort of gel that it acts to transmit the ions. So this is a very important component. Without that salt bridge, there's no reaction. So this whole component together is called the cell. And within the cell are what we call, or a galvanic, it might be called a galvanic cell, or and depending on the materials. But within that cell, there are the two components, each of the half cells, and the salt bridge. Additionally, and then some sort of electrical connection between them two. The location where oxidation is taking place. So this is our oxidation. That is called the anode. The place where reduction is taking place, that is called the cathode. So the anode and the cathode on the battery represents where the reduction and oxidation are taking place. So the cathode of the battery is where reduction takes place, and the anode is where oxidation takes place. These together are the simple components of the battery. Now, for this reaction to be complete, we need to balance it in terms of the number of electrons. Represents two silvers. So the balanced chemical reaction will be 2 silver ion plus magnesium goes to magnesium plus 2 plus 2 silver solids. And a total charge separated between them would be 2 electrons, which is important when we deal with the next component of this. So that's writing half cells.